Hello and welcome to another video on electrochemistry. In a previous video, you saw that we built a galvanic cell. That particular cell was made out of zinc solution and a zinc electrode and copper +2 solution and a copper electrode. And then the schematic showed how they were connected with an external wire between the two electrodes. And there was also a salt bridge that connected the two beakers together. And one of the features of the galvanic cell that you saw was the fact that it put out 1.10 volts. Now that video didn't go into too many details about where that 1.10 volts came from, and that's going to be the goal of this particular video. So in order to do this, what we have to talk about is an idea referred to as the standard reduction potentials. So we're in section 4 of the notes. Now, the standard reduction potentials, they are all relative to a particular reduction reaction. That is, they are relative to what is referred to as the standard hydrogen electrode, the SHE. And by definition, that particular half reaction, namely the reduction of H+ ions, is going to be assigned a value of 0.00 volts. And all the other cell potentials that you're going to see throughout the rest of this unit are relative to that value. It's kind of like how the atomic masses of the periodic table are all relative to the isotope carbon-12 being assigned 12.0000 atomic mass units. Then all of the other masses are relative to that. So all the values of voltages that you're going to see here in the rest of this unit are relative to the fact that the H+ reduction has been assigned a value of 0 volts. Now, what do I mean specifically when I'm talking about the hydrogen reduction? So here in question 15, the reaction we're talking about would be a couple of hydrogen ions in the aqueous phase being reduced by a couple of electrons to form hydrogen gas. And so this is going to be given a voltage of 0.00 volts. Now, let's talk a little bit about where these reductions come from and put this in context to some other reductions. So I'm going to go ahead and shrink down my notes and put them off to the side for just a moment so I can show you the standard reduction potentials in aqueous solutions. So this chart here is available on the Schoology page, and you can go ahead and download it. I would probably do that now and have a copy of that handy as we go through the rest of the conversation here. And really, you're going to want to have a copy of this chart handy throughout the rest of the unit because you're going to do quite a bit of referring to it. So if you'll notice right about, let me scroll down just a little bit, right about here is that standard hydrogen reduction and its assignment of 0.00 volts. And you can see that there are potentials above it with all positive values and potentials below it with all negative values. We're going to get into the importance of that sign in a little bit. But what I want you to notice about this reduction potential chart is, of course, all the reactions are listed as reductions. You can see on the left side of the reaction arrow, everything here is a reduction. Okay, and these are under standard state conditions, so 25 degrees Celsius, and the solutions are at 1 molar. The gases are at 1 atm. All right, so you can see we have a lot of values here, and so we can do a lot of combinations of reductions and oxidations to build our galvanic cells. So what I want to do is talk about how exactly we form the 1.10 volts for that copper zinc. So let me bring back the notes here. And what I'm talking about is we want to calculate the cell potential for this reaction here that you saw in the previous video. So what we need to do in order to get this value is we have to track down the potential for copper 2 to form elemental copper, and we're also going to look up the potential for zinc 2 forming elemental zinc. Now, I know you might start to get confused here because in our reaction, yes, copper 2 is going to elemental copper, so that's reduction. But of course, in any galvanic cell, you also have an oxidation. And in this case, we have the zinc going to zinc 2. But that chart I was showing you that I'm going to go back to in a moment here, that only lists reductions. So what are we going to do about that? Well, we'll get to that in a moment. So first, let me just track down these values. So let me shrink and move out of the way and come back here to the chart. So we're looking for copper 2 going to copper. So where is that guy? It's right here. Here's copper 2 being reduced to elemental copper, and that goes for 0.34 volts. Okay, so let me go ahead and put that on our notes here. So the copper 2 to copper, that is 0.34 volts. And then I need the zinc 2 to zinc reduction. So let me get my notes out of the way again. Come back here, and we're looking for zinc 2 to zinc. And that is right here, kind of in the bottom third of the chart. Zinc 2 to zinc at negative 0.76 volts. So as a reduction, going from zinc 2 to zinc is negative 0.76 volts. So let me put that back on our notes here. So this value here is negative 0.76 volts. Okay, so then as you can see here in question 17, in the reaction, yes, copper 2 is undergoing a reduction, but the zinc 2 is not. So what we have to do is calculate the potential for the zinc being oxidized while the copper is indeed being reduced. So the way you do these calculations is you find the cell potential by and E cell. A lot of textbooks abbreviate cell potential using the Greek letter epsilon, that kind of squiggly E symbol, and so I might casually refer to it as squiggly E as well. The way you calculate the cell potential is you get the cell potential of the reduction, and you can, depending upon how you want to treat this, there's a sign issue here, and I'll walk us through it. But essentially what you're going to do is subtract from that the cell potential of the oxidation, okay? And this sign can be a little bit tricky, so let's walk through it. All right, so I do have then my reduction. My reduction is copper 2 to copper, so that's my 0.34 volts. Now, my oxidation is zinc to zinc 2, but I have, of course, here the reduction from zinc 2 to zinc. So in order then to figure out what the cell potential is for the oxidation is, I need to flip the sign and add the potentials together. Or the way I wrote it here, take the opposite of the reduction for that oxidation. I know that can be kind of confusing, but here's essentially what we do is we're going to go ahead and add to this value the opposite value of the reduction for the zinc 2, namely 0.76 volts, positive 0.76 volts. So let's not get confused. You'll have the reduction potential that you look up right off of the chart, and then you have to flip the sign to find the actual value of the oxidation for the other half of the reaction. And when we put these together, that's how you get that 1.10 volts. All right, so let me go back to the chart and walk through that one more time. So my reduction was copper 2 to copper. So copper 2 to copper, I'm going to leave this half reaction and that value alone, 0.34 volts. But the oxidation is right here. It's actually going backwards, would be a better way to think about it, right? It's going zinc to zinc plus 2. So I have to flip the sign on that potential because it's written as a reduction on the chart, but I need it as the oxidation, so I just simply flip the sign. It's kind of like what you do when you're talking about delta H's of a reaction. And if you flip the reaction, if you make it go in reverse, then you're going to flip the value of delta H. So that's what we're doing here. Take the zinc to zinc 2 oxidation, and you merely flip the sign, and then go ahead and add those two potentials together to get that 1.10 volts. Okay, so let's go back to our notes. So that's our 1.10 volts for that particular reaction. Let's go ahead and figure out then how we would calculate the cell potential for a galvanic cell reaction that we haven't talked about yet. So here's another one. Iron 3 plus tin 2 makes iron 2 and tin 4. So I have to look up the reduction of iron 3 to iron 2. So my first step here is going to be to find the cell potential. I'm going to look up the iron 3 to iron 2 reduction. Okay, so let's go ahead and find that on the chart. Iron 3 to iron 2. Where are you? Iron 3 to iron 2. All right, there's iron 2. There's iron 3. It's right here. Iron 3 to iron 2. That has a potential of 0.77 volts. So let's go ahead and move that value over to our calculation. Okay, so that was a value of 0.77 volts. Now, if you've been paying attention, you might say, whoa, hold on, Dr. Crane, you're about to make a mistake because there's 2 irons here, okay? Shouldn't I multiply this voltage by 2? I'm actually not going to do that. Yes, there's a 2 there, but I'm not going to multiply the voltage by that coefficient. I'm going to get into a little bit as to why we do that at the end of this problem. All right, so there's the iron 3 to iron 2. So now let's find what was it, tin 2 to tin 4. So where is that tin reaction? It's right here. Here's tin 4 to tin 2. Of course, though, I need it as the oxidation, tin 2 back to tin 4, so I'm going to flip the sign. Okay, if I reverse the reaction, I definitely will flip the sign. If I multiply the reaction by a coefficient, I'm not going to multiply that through. I'll get to why in a moment. So I need to then put in a negative 0.15 volts into my calculation down at the bottom here. So I'm going to add negative 0.15 volts, and that gets me a total of 0.62 volts. Okay, so this particular redox reaction will produce 0.62 volts. Now, that's actually a worse result than I had for the iron and zinc and copper battery we made before, the zinc and copper galvanic cell of 1.10 volts. So this will put out voltage, but it's not going to do as good of a job as the copper and zinc reaction was going to do. But here's a couple of keys. Both of these have positive potentials. Okay, the sign here for both is positive. For thermodynamic reasons we're going to get into in a later video, for galvanic cells whose entire purpose is to do a chemical reaction to release a voltage to the surroundings that you can then do work with, like turn on a flashlight, power an iPhone, something like that, we have to have positive voltages. A positive voltage means that the electrochemistry, the redox chemistry, is spontaneous, i.e. the delta G is negative, and we'll see that connection in a later video. So all galvanic cells should have a positive voltage when you do this combination of the reduction with the oxidation. All right, let me go back to the chart and talk about the issue of not multiplying the half reactions by any balancing coefficient. So we saw in that iron example there were 2 Fe3s, but I didn't multiply that 0.77 volts by a factor of 2. That is because cell potentials, all right, these potentials, these are what is referred to as an intensive property. Intensive property. And what that means is it only depends upon what the species are, not how much of them there is in the system. So whether you have a milligram of iron 3, a gram of iron 3, a kilogram, a ton of iron 3, it's going to produce that 0.77 volts, regardless of how much you have, because it just matters that it's iron 3 turning into iron 2. Now, the larger quantities, what they will be able to do is provide that particular value of voltage for longer. And so the comparison here would be to batteries. You probably have in your house AAA batteries, AA batteries, and maybe even some C and D batteries. All of those batteries, if you look at the labels, they all produce 1.5 volts. The only difference between a AAA, AA, C, and D batteries we get larger in size is the amount of time, the amount of power, right, the amount of voltage over time that those batteries could produce. The larger batteries will produce that 1.5 volts for longer. So you put those D batteries in something like a powerful flashlight that you want to be able to turn on and use, over the course of maybe several hours. And that might draw a fair amount of power. Whereas a couple of AAA batteries, you can put those in a remote control for the TV at home, because the only time they really require power is when you're pushing the buttons on the remote, and that's a pretty low energy intensive process. So you can get away with having a small remote which requires smaller batteries that's more convenient to hold and use in your house. So cell potential is an intensive property. It doesn't matter how much stuff there is, it just matters what it is, and that will dictate the cell potential. So keep in mind, we want, when we add the reduction to the oxidation for galvanic cells, we have to get a positive value overall. All right, we'll leave it at that, and we'll get more into the thermodynamics of cell potential and other aspects of electrochemistry in later videos.